So I promised you some properties. There's a bunch of them. One of them is that it's useful, and that in particular it's useful for large state spaces. And the reason that that works, right, is that I don't have to actually look at all the states, do all of the value iteration for everything. I basically just kind of do it as I go along, and I only visit the states that I need to visit given where I happen to be in the world. There's some downsides of this, and one downside is depending upon just how much randomness there is in your transition model, you need lots of samples in order to get a good Q hat. But you know what? That's true anyway. If you have many states, then you're going to have to do a lot of visiting to figure out what's going on, usually. So this is the sort of, I think it's kind of intrinsic to the problem. Now, of course, if you don't have a lot of states, you still end up generating lots and lots of samples because of the way Monte Carlo works. Luckily, it's relatively inexpensive to do in most cases, at least most of the cases that we worry about. And in the end, despite all that, it has another good feature. I really like this feature. It's my favorite of its features, is that the planning time is actually independent of the number of states that you have.
Oh.
That's why it's useful for large state spaces.
I see. I mean, I guess if there's a lot of states, do we have to expand like a fixed percentage of them to know what to do?
Well, sure, you have to. That's how you're gonna generate your samples. You're gonna have to generate lots of samples that way. So yeah.
But then it's not independent of S.
Well, it is independent of S. That's one of the cool things about Monte Carlo tree search.
No, I know, but what you had said was what I asked was, so that means that as the state space gets bigger, do we have to expand? Or do we have to expand a fixed percentage of the state space?
Oh, you said percentage. I'm sorry. I didn't turn that into percentage. I'm sorry. So the answer is no, because if you did, it would depend upon the number of states.
Okay, but how could that be? How could it be that the state space gets bigger and yet we don't have to look at very much of it to know what to do?
Well, that's because you're really only going through, you're executing through the world. And the trade-off happens in the other bullet, which is the bad thing about MCTS.
It kind of reminds me of, like, I don't know, election surveys. That's probably not the right word. But this sort of idea that you can actually get an idea of how many people are voting, no matter how big the country is, by just surveying a fixed number of people.
Right, so long as they have properties that are consistent with that are representative. And so long as you can get a representative sample of the states and the actions, then you're good.
That's really interesting.
Right. Now, of course, that's going to depend on, so to me, what's going to drive that is going to be how much randomness and entropy there is in the transition function. Right?
I see.
Because if it's completely deterministic, you don't have to do a lot of samples at all.
Yeah, that would make sense.
But there's something else that drives how expensive Monte Carlo tree search is, which is the fourth bullet that I was about to write down before you asked me this complicated question, which is that the running time
is independent of the size of the state space.
It's independent in the sense that it's exponential.
Wait, in the size of the state space?
It's exponential in the effective horizon.
So you're saying it doesn't matter how many states are in the state space, but it does matter how far into the future you need to look to make a decision.
Yes. And of course, the tree itself is growing exponentially. So you're going to need to have more and more and more of those samples to make it work. Actually, due to Kearns and his colleagues, we actually know exactly what the running time is. It is big O of the size of your action space, which makes sense because that's your branching factor. And, I need another variable here. Let's call it X, which is how many steps you're going to actually run the thing for in that loop that I did before, raised to the horizon.